Hi, welcome to Chemistry 1001, Thermochemistry and Thermodynamics. This little topic I'm going to talk about how to make Hess's law useful. Hess's law is great because it allows you to calculate delta H's, whether reactions are exothermic or endothermic, by adding together other reactions with appropriate stoichiometric coefficients. The problem is, if we want to know delta H for a particular reaction, we need to have a whole lot of other reactions that we can add together. And we need to know the delta H's for all of these reactions. So what we need to do is have a table of standard reactions. And that's what we're going to talk about today. Standard states and standard reaction enthalpy. So the symbol we use for that is delta H, R or RXN for reaction. And the standard symbol is this little circle with a bar across it, meaning to say somehow it's standard. Otherwise, it's just a delta H of reaction for any kind of reaction. So in order to introduce this idea, I have to introduce what a standard state is first. What is it? The standard state of a substance at a specific temperature, we don't know exactly what that is its pure form at 1 bar pressure, which is 100 kilopascals. Note, 1 bar pressure is not 1 atm, it's 101.325 kilopascals, that's 1 atm. The bar unit of pressure is derived from the triple point of water, but we won't go into that. So that's the standard state of a substance. The standard state of a substance is not necessarily its lowest energy form, not necessarily its most stable form. For example, carbon has two pure forms, two allotropes. One of the forms of carbon is graphite, otherwise known as soot. And the other form is a little bit more valuable, that's diamond. Both of them are forms of carbon. In the first form, the carbon forms sheets of hexagonally arranged carbon atoms, and these sheets can slip over each other, making graphite a very useful lubricant. And the other form of carbon is diamond, where the carbons are arranged tetrahedrally around each other in a very tight periodic and infinite network. There's no way the carbons can slide over each other. In fact, diamond is one of the hardest materials known to man. Both of those are pure forms of carbon. Both of those would be allowed standard states for a substance. One of them is a lower energy form and one is a higher energy form. I'll leave you to look up on Google which one of those is more stable. In other words, does diamond decay into soot, or does soot eventually turn into diamond? Which one of those two is more stable? Of course, it's a very slow process. So that's the standard state. Standard states usually mean temperature 25 degrees, but you have to say what particular temperature. Sometimes it means 0 degrees. Standard state doesn't mean any particular temperature. Note, the enthalpy of a substance in its standard state depends on the temperature. Obviously, if you increase the temperature of a substance, you increase its energy. Obviously, the atoms are moving faster inside, so its enthalpy changes, and therefore the heat of reaction depends on temperature. The higher the temperature, the more energy a substance has, and so delta H for the reaction changes with temperature. Okay, so that's the standard state. And when we talk about reactions between substances in their standard states, we have standard heats of reaction given by this symbol in the square bracket. So delta HR for a reaction is the enthalpy change where reactants and products are in their standard states. Okay, great. That's fine. There's another definition you need to know about, and that's reference states. Reference states only apply to elements. The reference state of an element is its most stable state at 1 bar pressure. at the specified temperature. Okay, so a reference state applies only to an element, and the reference state is a standard state. It's the most stable form of an element, the most stable form of the standard state of an element. So there are various standard states of elements, and the reference one is the most stable one. So they're very similar ideas, and the reason why we need this is to define, for example, atomization energies. Again, reference states can refer to any temperature. For example, and here are some examples. For nitrogen, the element nitrogen, the reference state is nitrogen gas at 25 degrees C. For mercury at 25 degrees C, it's liquid. For carbon at 25 degrees C, it's graphite. Graphite is more stable than diamond. Oh, sorry, I told you the answer. So apparently diamond eventually decays into soot, given enough time. Sorry about that. Okay, normally the reference state's at 25, but it's not necessary. So the standard enthalpy of formation, and this is the important thing about reference states, is the enthalpy to form 1 mole of the compound from its elements. Delta heat of formation F, that's the delta, meaning the heat of formation for the reaction. And what is the reaction? It's the formation of the particular compound, can be water, can be diamond, or whatever. Formation of water, for example, from elements of hydrogen and oxygen in their reference states. In this case, hydrogen gas and oxygen gas, because those are the two reference states for hydrogen and oxygen at 25 degrees C. That's what this thing represents. Heat of formation, and be aware of the other one, standard state, the heat of reaction relative to standard states. Okay. Why is that useful? Okay, let's look at how we can use the heat of formation to calculate heats of reaction. And for this we need Hess's diagram in a different kind of form, and the formula is very simple. The heat of reaction for any chemical reaction is the heat of formation of the products minus the heat of formation of the reactants. These are heats of formation relative to the reference element states. And here's the diagram that shows what's going on here. From the elements in their reference states, we can form reactants or we can form products. Therefore, we can form from the elements the reactants, and from the reactants we can form the products. So there are two different ways we can form the products. We can go from the elements directly to the products, or from the elements plus delta HF plus delta HR to heat of formation of the products. And if you think about this, delta HF plus delta HF for the reactants plus delta H for the reaction equals delta HF for the products. That's just this equation over here, except we have a minus sign. Instead of having the reactants on the left-hand side, we have put them on the right-hand side. So that works for any heat of reaction at any temperature, whether standard or not. If you want the standard heat of reaction, this equation applies. You just put a little O and a dash on either side, meaning to say that this equation also holds for products and reactants in their standard states. You knew this from school, and this is just another way to tell you what you already know. See you later.